So we were lucky enough to discover light echoes of the explosions of Eta Carinae. What a light echo is, when you have an explosion in the sky, you originally will detect it as the light travels toward Earth. But the light actually travels from the explosion site in all directions. So it might happen that some of the light will encounter a region of dust, which will then reflect the light back towards Earth, and now you get to see the explosion again at a later time. The difference in time between the two events as registered on Earth has to do with the length of the path that the light has to travel. So the original explosion is seen after the time that it takes the light to travel a distance d, and the distance that now the light has to travel is longer, so we'll get to see again later. And in this case, about 170 years later, because the original region of dust was about 170 light years away from Eta Carinae. So the great thing about this is that now we get to see the explosion with all the modern equipment that we have. In the 1840s, we didn't have spectrographs, we didn't have CCDs. So now we get to see it, and we get to record the explosion with modern equipment and study in great detail with all the extra knowledge that we have about astrophysics that we acquired in the last century.
Eta Carinae is a normal star in the sky in the southern hemisphere, but in the 1800s, it actually got to be the second brightest star in the sky because something happened. It turns out it's a binary star system, and it's one of the most massive star systems we know about in the Milky Way. So it's two huge stars in orbit around each other, and some kind of explosion happened. That's kind of all we knew for a little while until we started observing it with more modern instruments like the Hubble Space Telescope, and we can see that there are these two lobes of gas coming out of this thing, and it's because there's some massive mass loss from this system. It's two big stars, but about 10 or 20 solar masses has been blown out of the system. We didn't quite know what that was until we were just able to re-observe the explosion that happened in the 1800s. By using a light echo, and now we can observe it with modern equipment and watch it happen in real time. So massive stars are really rare. There are only a few of them in the Milky Way, and they live for a really short amount of time, and so we don't always get to see them. So when something happens with a massive star, like it loses a lot of mass, we really want to watch that happen, but we can never catch it in the act. This time, by re-observing the explosion, we actually can see a massive star in the process of losing mass for the first time, and we could figure out what could cause a huge star to really lose a significant part of its mass. And it turns out it's not just some normal event. People thought maybe stars just gently slough off their mass, but no, it really was some kind of big explosion. That's one of the things we found out from this data.
So when we found out that light echoes of Eta Carinae had been discovered, we started following them with our telescopes. We have a 2-meter telescope, the Fox Telescope South, in Siding Spring, Australia. And we've been observing the explosion for about a year now at a monthly cadence. That is, once every month, we point the telescope to the explosion and we look at the light curve. So we can reconstruct how the light curve of the event, how the light changed in time. That allows us to make sure that we're looking at, indeed, the 1843 event, where Eta Carinae exploded and released all that mass. Also, larger telescopes have been observing the spectra of Eta Carinae. A spectrum is the light emitted split in frequency. So you're kind of like looking at a rainbow of the explosion, and you see how much blue light versus how much red light is emitted. By looking at how the spectral looks like in detail, we can tell what the temperature of the explosion is, which tells us a lot about the physics that was going on.